Welcome to section 2.2, differential equations. So in this section, we've got a lot of ugly algebra, but more importantly, we're looking at the right-hand side of the differential equation, and we're trying to determine where are the critical points, and around these critical points, what's going to happen if we change the initial conditions. Is the critical point stable or unstable? So, looking at our first problem, we have dx dt equals x minus 9. Alright, so the right hand side here, when is it 0? Well, it's 0 when x is 9. Okay, so x equals 9 means that dx dt is 0, so the function would be constant. So, if my initial condition is 9, then the solution will remain 9 for all time, because x equals 9 is a critical point. But what happens if I pick my initial condition to be 8 or 10? On either side of the critical point, what's going to happen? Is the solution going to increase to 9, or is it going to decrease and run away from the 9? And what happens on the other side? Well, let's take a look. If x is 8, then 8 minus 9 is less than 0, which means that the derivative is negative, which means that the solution is going to be decreasing and moving away from 9. If my initial condition is 10, 10 minus 9 is positive, the derivative is positive, and if the derivative is positive, then the function is increasing, and it's moving away from the critical point of 9. So you can see that in this particular picture here, if I start below 9, the function is going to be decreasing forever. And if I start above 9, the function will be increasing forever. So if we now get into the algebra of actually solving this, then let's see, I'm going to separate the problem. We get x of t is 9 plus c e to the t. And so I'm going to call x 0 when time is 0. I'm going to leave that number there unspecified as 9 plus c. So c is x0 minus 9. So you can see that the solution here clearly depends upon this particular value, which is your initial starting point. If we look at the flow diagram, here in blue is 9. So here's the 9. If I start at 8, my solution is going to be decreasing forever. And anywhere I pick under 9, the solution decays. And if I pick something above 9, then the solution will follow the flow field and grow. And again, if I pick 9, it's going to stay constantly 9 forever. Alright, in question 2, we have a similar situation. Except here I've got x minus 19, that quantity squared. When is the function 0? Well, when x is 19. So 19 here is my critical point. And so again, what happens if my initial condition is less than 19 or bigger? If it's less than 19, because of the squaring, it's going to be positive, and the function is going to be increasing. All right, so if I start under here, the function is going to be increasing up to 19. What about if I pick a number bigger than 19? Well, this item is still going to be positive. The function will be increasing, and so it's moving away from the 19. So one side is growing and going to stop at 19, and the other side is going to be growing forever. So 19 is not stable, and so the solution will increase. It is semi-stable because on this side it does have some stability in that it is increasing and will stop at 19. To make the graph a little easier, I changed the problem. Instead of being 19, I made it 3. And so here's the 3. All right. And so if I start bigger than the critical point, it's going to grow. And if I start under the critical point of 3, like at 2, then the function will continually increase and approach the critical point. All right, so we now try to solve this. On the right-hand side is easy. That's t plus c. On the left, I need to use substitution. All right, so we do that. And so again, I'm going to try to solve this and just let x 0. We're going to call it x0. Now that makes the algebra very messy, but it does at least show us how the solution depends upon that choice of the initial condition. So by making that one times 0, I get this for c. And so now it's a question of trying to clean this thing up and get x by itself. All right, so first off, I tried to combine this by getting a common denominator. All right, pulling them together over the common denominator. And so now I've got 1 over x minus 19. I could cross multiply, but I'm just going to flip everything over. So I get x minus 19. All right. So I can get x alone by adding 19 to both sides. All right. So got that. Again, I want to get a common denominator. All right. So the algebra is a bit messy. All right. So it's going to be this item over itself times the 19. All right, so I did that, and now I'm looking to see, well, these 19s would cancel over the common denominator. And so I can get my solution for x of t, where the solution depends upon time. And it also shows you what happens if you change the initial condition. All right, in question 3, we have f of x is x cubed minus 3x plus 2. And so that's factorable, a quadratic equation, and so I get x equals 1 and 2. So the differential equation has 2 critical points. And if I graph f of x, what I see by that is here's where it's 0. If I started off bigger than 2 on this side, that means the function is positive. If the function is positive, the derivative is positive, which tells me that my solution will be increasing. So if I start off bigger than 2, the function will continue to grow. If I start off under 1, well, in that case, the function is again still positive, derivative is positive. So my solution will be increasing. Increasing not forever, but would increase up to 1. If I start in between 1 and 2, in that case, my function is negative, so the derivative is negative, which means my solution will be decreasing. So putting all that together in a picture here, under 1, we reach 1. Above 1, we decay toward 1. Around 2, though, notice things are moving away from 2, so it is unstable. And so looking at the flow field, here's 2. So if I start somewhere bigger than 2, the solution will grow. And if I start in between between 1 and 2, it's decreasing to 1. And if I start under 1, then it's increasing up to 1. All right, so we're going to solve this by separation. Left-hand side is partial fractions, so I know I can expand this as something over x minus 2. B over x minus 1. Right-hand side is easy. So these using substitutions are just natural logs. And so we'll be able to go on if I can solve for A and for B. All right, so looking at the partial fractions, I'd multiply through by this denominator. And then I can pick different values for x. So if x is 1, I can solve for b, and b is minus 1. And if I let x be 2, then I can solve for a, and a is 1. All right, so plugging that back in here for a and for b, we get a difference of 2 logs, which we've seen before by properties of logarithms, that's the log of a division. Take e of both sides, so I can get the x by itself. All right, so on the right, I get an e to the t, I get an e to the c, and we just call that c. All right, and so x at times 0, again, we're just calling x 0. So if I plug in 0 for that and x 0 here, I get this relationship for c. All right, and so I've got this ugly thing here, and I'm going to need to try to get x alone. All right. So first off, I cleared away the denominator, multiplying both sides by x minus 1. All right, now looking at that, well, let's see. I'm going to distribute this guy into this. I'm trying to get the x's together. So I'm going to take this term left, get the 2 to the right. All right, when I move this term to the left, I'm going to factor a x out. So I'm getting x alone. On the right, I'm going to get a common denominator. All right, so looking at that, I've got this term here. This is all over this term, x0 minus 1. All right, so looking here with a bit of algebra, we finally get to our solution, which depends upon x0 and on t. All right, so on this previous step here, I multiplied through by x0 minus 1 to cancel all these denominators, and then divided by that term for the final step. Question 4. All right, we have this differential equation but now they're throwing in a H here, which is a particular rate of harvesting. And so the question is, how does H change the nature of the problem? All right, so looking at this, I multiplied the 1 over 24x in. And then I'm looking at this and I'm realizing that it's just a upside down parabola. All right, so what I did was I said, okay, well, what if I change different h's, and well, what does it look like? And so I made different graphs here with different values for h all the way down. And so when h is 6, we have one critical point, and that's when x is 12. And notice as h gets bigger, there are no critical points. We are under the axis here. All right, so as h goes down, we're going to get more critical points. 2 positive here. As h gets smaller and smaller, we're picking up some negative critical points. And so what I did was I took that, I used a Wolfram alpha to solve this quadratic equation to figure out how does h depend upon this thing. And so what I get is my solutions are going to depend upon h in this way. And what do I notice? Well, if 6 minus h is greater than or equal to 0, which I need that to happen to get the square root to give me real values, that I need h to be less than or equal to 6. So if h is smaller than 6, we saw 2 critical points. If h is 6, all right, plug in 6 here. This is the square root of 0, and all of this goes away, giving me one critical point of 12. And if h is bigger than 6, remember my flipped over parabola was under the axis, so no real number critical points. All right, so I'm looking further, so let C be one of these critical points, and I'm wanting to know when is my function going to be 0. All right, so looking at all that, I set all this true. A bit of algebra. I'm going to complete the square on the right-hand side here. B is minus 24. My factoring term is half of B. The part to add in is the B over 2 squared. So what I get is a relationship, a bifurcation picture, which depends upon C and H. Okay, so we look at this particular parabola on its side. If C is 12, my one critical point, all right, that happens when H is 6. And so we see as different H's what happens to our particular critical points. All right, in question 5, we have a logistic model, a population model. Except in this case, we're going to change it up a little. And because of fishing in this lake, the fish are going to be removed from the lake at a particular rate. And that rate is hx, where h is a positive number. So we're going to take our normal population model. We're going to subtract off hx from our removal from the lake. So the fish are being harvested. So the question becomes, well, what happens if we have different starting conditions? All right, so first off, they wanted us to show that if h is between 0 and km, where's m? M is here, k is our proportionality constant. If my removal rate is between these two numbers, the model is still logistic. All right, so here's my model. I multiplied by kxn. All right, so looking at that, then I factored out a kx. All right, so my model looks like the following. Notice m minus h over k is just a constant, so I'm going to call that m tilde, and I'm going to call the k in the front k tilde. So notice this still looks like a logistic equation. And so if it's a logistic equation, this m tilde is the carrying capacity. And so the carrying capacity is m minus h over k. And so if h is km, put in km here, then m tilde is a critical point of this particular equation. And so that would give me this model. All right, and so x equals 0 is a critical point in this model. And so if I pick something bigger than 0, this derivative is negative and decreasing. Now, what if I pick some conditions here where here is my m tilde, which is m minus h over k, my new carrying capacity that was reduced. What if I pick something bigger than that number but less than 0? Well, in that case, the derivative is greater than 0, and the function will be increasing towards 0. And if I pick something less than that, then this will be decreasing. And so, depending upon how this works out, the 0 is stable, and as time goes to infinity, we are fished out, and the capacity of the fish will decrease to 0.